Thanks so much, Zoe. And first of all, thanks so much to the organizers, Michal and Simon, to be invited to speak here. Um, it is actually quite a sentimental moment because, as Michal mentioned, 2 years ago, I spoke at the first installment of this conference, and back then it was actually the first time I spoke to a bigger audience about our efforts in shielding. And that was a very exciting moment for me. And now, 2 years later, a lot has happened, and I'm very excited to tell you about our work towards Bose-Einstein condensation of dipolar molecules. So the broader efforts in ultracold molecules are very much in a transition that ranged over the last century to gain control over ever more complex quantum systems, perhaps starting with quantum spins, electrons, photons, atomic ions, neutral atoms, and now molecules. And in some sense, on this sort of endless frontier of quantum control, molecules are now the next item on the list. And, besides any specific motivations what to do with them, I think it will be just extremely exciting to see which new opportunities in science and technology open up with them. For neutral atoms, Bose-Einstein condensation was an extremely important achievement because it was actually the first time it was possible to put thousands, later millions of atoms in the exact same quantum state, not only the exact same internal state, but also the exact same state of motion. And that really kicked off a whole wave of research and enabled a lot of applications like quantum simulators, quantum computing, and ultra-precise clocks, in the aftermath and the reverberations of this achievement. Looking back in history on how quantum control started, one point to mark is perhaps the work of I.I. Rabi, who about 90 years ago, perhaps flipped for the first time in a more or less controlled way a quantum spin. That was a nuclear spin in lithium atoms. And actually, if you look at the work, it's quite interesting to note that this was not done in atomic lithium, but actually in lithium fluoride and lithium chloride molecules. So the quantum control of molecules has a very long tradition, and it basically takes us until today to fully achieve it. And that is because there's not only nuclear spins in molecules, but also a lot of other degrees of freedom, such as rotation, vibration, and electronic states. And when talking about quantum control of molecules, we are particularly interested in the lowest internal quantum state, the low vibrational ground state, because there, at least on a single molecule level, we can hope to have long lifetimes. On the theory side, there have been proposals what to do with such molecules for more than 20 years now, including creation of novel many-body quantum systems, simulation of quantum magnetism, precision measurements, quantum chemistry, quantum computing, some of it already covered at this conference also. And also on the theory end, it was early on understood that it would be particularly interesting to realize dipolar molecules. So quickly reminding ourselves how dipoles interact. So they have an interaction that goes as 1 over the distance cubed, and when dipoles meet side by side, they repel each other. When they meet head to tail, they attract each other. And such an interaction is ideal to create strongly interacting and highly entangled many-body quantum states. Compared to other dipolar systems in atomic physics, dipolar molecules actually occupy a very interesting spot compared to the relatively weakly dipolar magnetic atoms and the extremely strongly dipolar Rydberg atoms. With dipolar molecules, we are at a spot sort of at the intersection between weak and strong interactions. And that is really, on a many-body level, the point where we can expect interesting quantum phase transitions to happen. The door to this field was opened by the extremely amazing work of Debbie Jin and Jun Ye more than 15 years ago by now, who taught us how to assemble molecules from ultra-cold atomic gases, and also that really kicked off a wave of research around the world. The list is growing of assembled molecules at microkelvin temperatures and lower. But all these experiments also realized that there are fast inelastic losses when the molecules collide. And although in the early experiments already, the temperatures of the gases were on the microkelvin level, it was very hard to cool further So they stayed non-degenerate because for further cooling you would have to do evaporative cooling, which requires collisions, and that would not actually work out due to the inelastic losses. So that this situation may change became clear a few years ago with a wonderful work showing shielding methods in ultra-cold molecules, including resonance shielding, microwave shielding, first shown in John Doyle's group with 2 calcium fluoride in a tweezer trap, and then microwave shielding on NAK molecules at MPQ in Munich. And in these earlier efforts, it was shown that you can suppress inelastic losses roughly by a factor of 10. And for fermionic molecules, that actually allowed evaporative cooling to quantum degeneracy. So natural question is, what about bosonic molecules? Well, in bosonic molecules, an issue is that the inelastic losses are roughly a factor of 100 larger than in fermionic molecules, because fermions benefit from the Pauli principle, or in other words, they have to overcome a p-wave barrier to undergo an inelastic collision. While for bosons, that barrier doesn't exist, so the losses are a lot higher. So in some sense, the question, whether we could achieve a degenerate gas of bosons boiled down to the practical question if we would be able to reduce losses by a factor of 100 to 1,000. So that is where our experiment comes in. Our sodium-cesium molecules are bosons. They have a dipole moment of 4.6 dBi. That was a key reason to pick this molecule. And they can be controlled with external electric fields, which controls the dipole moment. And if you plug in this 4 dBi and calculate the dipolar length for this molecule, you get a number that is in the tens of micrometers. If you compare that to typical interparticle spacings in our molecular samples, which are on the micrometer level, you already see there's a chance to get into the really strongly interacting regime. So let's get to the creating BEC part. So that was an effort that happened over many years, and I will try to give you a quick rundown of what we actually did to get there. So that started all in an empty lab about 7 years ago. And we built laser systems to laser cool sodium and cesium. First created overlapping BECs of sodium and cesium. So it's actually a very well-behaved mixture. So, the 2 species actually sit on top of each other, which was very helpful to make Feshbach molecules. We do that with a Feshbach resonance that sits at 864 Gauss. And it allows us to create gases of 50 to 60,000 Feshbach molecules at microkelvin temperatures. And then we do stir up to the absolute ground state with efficiencies up to 90%. And that essentially led us to have samples where the internal quantum state of the molecules is controlled. So we can create 10,000s up to 50,000s of sodium cesium molecules, all in the exact same internal quantum state. So now we want to continue working on controlling the state of motion. And here an important tool is microwave control. So initially we prepare the molecules in the rho vibrational ground state, so specifically also in the rotational ground state. And from there we have 3 microwave transitions to go to the first rotationally excited state, sigma plus, the pi, and the sigma minus transition. And to sort of selectively address these transitions, it was already clear that we need an antenna that can actually produce very clean polarization microwave fields. So to this end, in particular to create clean circularly polarized microwaves, we developed what we call a cloverleaf microwave antenna. And that allowed us to get very clean circular polarization with ellipticities of 2 degrees, or actually by now probably even quite a bit less. If you use this antenna to drive resonant transitions in the molecule, resonant rotational transitions on the sigma minus and the sigma plus transition, we actually can drive Rabi oscillations, and we found that we can reach a Rabi frequency of 40 megahertz. So that is a very good number. We were very pleased to see it's possible to get this very strong coupling. And if you sort of translate that into sort of a quantum control, quantum information kind of language, you can run a Hadamard gate in 6 nanoseconds. And, with Simon's recent work on long rotational coherence times in molecules with rotational coherence times on the order of a minute, that basically would mean that you can run like 10 billion single qubit gates in molecules. So that's probably a pretty exciting frontier going forward. But for now, we are skipping over that and continue cooling. So after being able to control microwave fields to this degree, we implemented microwave shielding with a single blue detuned sigma plus microwave field. So you heard a lot about microwave shielding already yesterday. So the gist is that we create a collisional barrier at about 1,000 Bohr radii. And actually, when doing this shielding with a single microwave field, we also realized that due to the anisotropic polarizability in molecules, we have a single molecule effect of shielding. We mix the first rotational, the ground on first rotational excited state. And that means the molecules react differently to the dipole trap in which they are trapped. So we kind of mapped out this effect and found sort of in passing when doing spectroscopy between the dressed rotational states that you can also use dressing, microwave dressing, to engineer a magic rotational transition. So that was very, very nice to see and understand. And then we used the shielding to actually study the lifetimes. So we see with a single microwave field applied, we can increase the lifetime of the molecular sample by about a factor of 50. So we're extremely pleased to see that. It was basically a record at that time. Well, we tried to do evaporative cooling at this point in time, but then we got stuck at phase-space density of 0.1, where we would have liked to reach phase-space density of 1, where Bose-Einstein condensation is expected. And well, that was actually the point at which I gave the last talk here at this conference at September 5th, 2023. It's actually a special day for me. It was my birthday. Well, here we are. So what comes next is all things that are new since then. So what we sort of at that time already started understanding is what limited the evaporative cooling of the molecules with single shielding. And that was three-body recombination. Basically, when we apply a single sigma plus shielding field, the collisional potential is not a flat line and then a repulsive barrier. It actually has an attractive potential well here. And especially when the shielding is supposed to be very good, this well is sufficiently deep to support a bound state. And in that bound state, you can have recombination, three-body recombination. Two molecules go to the bound state. One molecule flies away, carries away the excess energy, and it turns out the molecules in the bound state actually get lost in our case. So it was kind of clear we need to solve this bound state problem. And figuring out how to solve it was the key to actually make a BEC. So what is the current situation? So we have our molecular samples, like 50,000 NACS ground state molecules in a dipole trap, and we apply a sigma plus rotating microwave field. And then we have this issue that, there is this attractive potential when the two molecules meet side by side, essentially. So, what could be a thought how to remove this problem? Well, how about we dress the molecule with another microwave field, the pi microwave field? And if you start thinking about it, there is a sign difference between the interaction of the rotating dipoles and of the vertically oscillating dipoles. So, so intuitively, you may think, this can be used to compensate this, compensate this repulsive side-by-side interactions of the vertically oscillating dipoles can be used to compensate the attractive interactions of the rotating dipoles. Well, that is sort of, the intuitive picture. So Thijs was absolutely instrumental to actually make us fully believe that this is actually working. So, with Thijs, with whom we closely collaborate for a number of years now, we figured out that, with combining these fields in the right way, you can create an all-repulsive potential with a flat line and then a repulsive barrier. And Thijs told you all about it yesterday. So in the practical implementation, a lot has to happen to actually make that work. So we have here our sigma field that's generated with a cloverleaf antenna. So there are 4 phase-shifted microwave outputs there. Then to generate a pi field, we have another antenna that comes from the side. But the 2 fields from the 2 antennae need to stand exactly orthogonal on each other. Or they need to be normal on each other. which is sort of geometrically never possible to achieve to a sufficiently good amount. So actually we apply another compensation field for the pi antenna, so we can tilt the microwave field so they are truly standing orthogonal on each other, and that turned out to be absolutely essential. So that was exactly what we were working on during the last Warsaw conference. So just to visualize for you what's really going on here with this double microwave shielding, I give you here a 2-scale picture of what's going on. So the molecule has a size of 8 Bohr radii, and the repulsive shield that we generate with the 2 dressing fields has a radius of 2000 Bohr radii. So that's a 2-scale picture. So, and now in this situation, we do evaporative cooling with a within the typical way, we hold the molecules in the dipole trap, and then we lower the depths of the dipole trap and evaporatively cool. And we do that now on a timescale that's very familiar from atomic system. It's a few seconds evaporation ramp. And if we do that, well, we can start looking at our clouds. After some initial cooling, we already reach a temperature of 40 nanokelvin. For precise thermometry, actually, just to add one more technical detail, it's very important that we can do time of flight expansion of the molecules. To that end, in our setup, we do vertically oriented stirrup beams, so the molecules can drop in the stirrup beam and be reverse stirrup just before imaging after their time of flight. So that was tremendously helpful to get really accurate temperature numbers. So here you still clearly have a Gaussian fit applied to this cloud, and it's a thermal gas. But if we cool further, we see that this distribution changes into a bimodal distribution, and a peak grows out of this thermal background, which signifies the appearance of a BEC. So that was the first time a phase transition was crossed with ultra-cold molecules into a BEC. So that was a big moment, and that actually happened on October 2nd, 2023. So some people may say, how could you be so uncertain about achieving it last time around this conference? But truly this, getting the microwave fields under control in a way that it really works, and especially not knowing for sure that it really works, requires quite some scrutiny to really make it happen. So if we plot the data that we took here on a graph from the evaporation, you see that the phase-space density of the molecular gas increases by roughly a factor of 1,000. So that was really tremendous, a huge boost over anything that had been done before with molecules. And the temperature goes down from 700 nanokelvin to 6 nanokelvin. And for the experts in the audience, an important aspect to make a BEC is actually that you want a weakly interacting gas. If it would be strongly interacting, also strongly dipolar, you would actually not expect BEC, you would have significant quantum depletion. And it turns out that, our interparticle spacings and dipolar lengths and S-wave scattering lengths work out such that we are truly in a weakly interacting gas. Also, the lifetime of the BEC turned out to be fairly long, larger than a second, and basically that can be turned into a number of a factor of 10,000 suppression of the losses in the molecular sample. So huge excitement when we got to this point. Misha was also at the last conference. And by now, the BEC is growing. So if you paid attention on the previous plots, the early BECs had like maybe 200 molecules in them. By now, we got even better in optimizing the compensation of the double microwave dressing in the practical implementation. We increased with that the evaporation efficiency to 3. It's as good as atomic evaporation, and that increased the molecule number in the BEC to 2000. So that's great because it enables single shot imaging, and we can take images of this famous trio of clouds crossing the phase transition. And we're also excited to hear that basically an adaptation of our method works also for sodium rubidium molecules, and we'll hear all about it from Dajun in the next talk. So let's get a little bit to exploring this system. So one question that came up early on is, how stable is the molecular gas when the dipolar interactions get stronger? I told you that in the situation of double microwave dressing that we use to make the BEC, we are actually on purpose dialing down the dipolar interactions by compensating dipolar interactions that come from the rotating dipoles and the vertically oscillating dipoles. So if you plot the dipolar lengths, we make the BEC actually where the dipolar length is close to zero. When we made the initial BEC, we were not so good yet to really dial that to zero, but now we got really good at it. So basically you get zero dipolar lengths. And then by imbalancing the microwave dressing fields, you can get finite dipolar lengths. And what happens then to the losses? That's the big question. So to that end, we take loss curves in the system, just holding the sample in the trap. And under certain conditions in this work, we found then we can reach lifetimes above 6 seconds. So that is really, really quite amazing. Very close to what you may see with atoms. We can also use these loss curves to identify the difference between 2-body loss and 3-body loss. So very happy that our signal to noise is sufficient to actually do such distinctions. That allowed us then to determine 2-body and 3-body loss rates as a function of dressing parameters. So it turns out the 2-body loss rate is always extremely suppressed, and in regimes where we can measure it, it's following exactly Theis's calculation. So kudos to that. What remains to be looked at is the 3-body loss rate. That's what's plotted here. So at the BEC point, we see this 3-body loss rate. With single microwave shielding, we see this 3-body loss rate. So there is already a factor of 1,000 reduction, but the question is what's happening in between. And it turns out that there is actually quite a plateau of extremely strongly suppressed loss. It actually turns out both 2- and 3-body loss are suppressed below our detection limit, which is set by the 1-body lifetime of about 8 seconds in our system. So we can basically not measure 2- and 3-body loss in this data here in this window. And then actually when the bound state enters again into the collisional potential, the 3-body loss comes up on either side. But that is great news because here in this window, we can tune dipolar lengths between 0 and 20,000 Bohr radii, which is a pretty hefty range. We can also use the loss rates that we measured, and conservatively estimate the highest density that would be stable in our molecular gas. We find that densities of up to 10 to the 14 or so would be stable in our situation. And if you take that as a foundation, you can calculate the ratio of dipolar interactions to kinetic energy that could be achieved in a degenerate gas in our system. We find that we can be able to tune that interaction parameter from 0 to 7 continuously in this stability window. So that's extremely good news for the study of interesting many-body physics. So let's get to that. What happens when we increase the interactions in our BEC? Well, I told you one way to tune interactions is using the balance of the pi and the sigma field. Well, another way to do that is to stay at the compensation point where we do the BEC, but turn the polarization of the sigma field into a slightly elliptical field. And that gives rise to dipolar interactions that break axial symmetry. So that's something, as far as we know, something very new. And it gives rise to an interaction pattern that looks like that, repulsive in this side and attractive in that side. And the larger the ellipticity, the stronger the dipolar interaction. So we can use this tuning knob now, apply it to our gas and look at our molecular sample in time of flight expansion. If we use close to 0 ellipticity, we basically get the expansion of a BEC. Here to the sides, you already see something pretty dramatic happens to the cloud. It gets elliptical. So that is electrostriction. We will hear a lot more about it in Hanel's talk, soon after. And if we increase the ellipticity further in one direction, we see something very dramatic happening to the cloud. The cloud shrinks, and in time of flight, it doesn't expand anymore. So that is a signature of a self-bound droplet. And if we rotate the direction of the interactions by 90 degrees, we see that the cloud actually splits up into individual droplets. And if you look in time of flight, also these droplets don't expand anymore in time of flight. So it's an array of self-bound droplets. So actually, side note is, first time I show this anywhere, we actually observed droplets before we observed a BEC. So the first time we saw a bimodal distribution was on September 18th, 2023, so just 2 weeks after the last Warsaw conference. But that wasn't the BEC yet, because if we would do time of flight, it would actually not expand. And what we learned on the fateful October 2nd was how to control the ellipticity of the microwave field to actually reduce the interaction and get an expanding cloud that expands compatible with the BEC. Okay, when it comes to droplets, it's actually an important question what holds them together. In magnetic atoms, usually the Li-Wang-Yang correction is applied to the Gross-Pitayevsky equation, and it seems to work reasonably well. But in molecules, we can enter regimes where this may not be obvious anymore, why this should work. So this will be an interesting question to address on the theory side. We can do non-equilibrium experiments in our sample. We can change the ramp speed with which we induce the interactions over 4 orders of magnitude of dynamic range, going extremely slowly on the second scale to extremely fast on the microsecond scale. And we see how a 1D array of self-bound droplets turns into something quite mesmerizing. And in all droplet formation in nature, the question of the role of non-adiabaticity always plays a role all the way back to looking into what happens in galaxy formation. So this is exciting to look at. Now, what we also did with the droplets is we tried to measure their density. And for that, we actually leverage our extremely fast switchability of dipolar interactions. We prepare the droplet, then rapidly switch off the shielding. We get universal two-body loss, and that allows us to get an idea of what the density is inside the droplet. And we actually find that the density from the BEC here increases by 2 orders of magnitude, more than a factor of 100, in the droplet to the 10 to the 14 level. So these are densities that we know from ultra-cold atomic gases. That's something quite dramatic. And still we get a lifetime of these on the order of larger than 100 milliseconds. So it's surprisingly stable. And actually, if you go through the numbers, you find that the interaction energy should be substantially larger than the kinetic energy. So this is probably the first time a strongly interacting molecular gas was created. And there's a lot of interesting fundamental questions of what the state of matter truly is here. Okay, just coming to a very brief outlook. I told you about the power of tunability of interactions with the microwave dressing fields. So it gives us control over, hard sphere radius or shielding radius, S-wave scattering lengths, and dipolar range. We can, non-adiabatically switch interactions of Loquet engineer interactions if we want, really changing the interaction radius extremely flexibly. It will be fun to study droplets more. A lot of predictions have been made, and perhaps the experiment will surprise us. Loading the molecules into 2D will be great, leveraging the strongly interacting capabilities and perhaps crossing the transition to a dipolar crystal. Putting them into a lattice and under a microscope will be certainly something of great interest. We can hope to reach high filling fractions and study interesting lattice models. Just want to highlight one thing. We also have a second effort on tweezer trapping. On tweezer trapping of strontium. So we can do all kinds of tweezer arrays using holographic metasurfaces. Just want to show you one thing because there are people working with molecules and tweezers here as well. We just used metasurface to make an array of extremely large size, a 600 by 600 tweezer array. So you're zooming into it and we're zooming out of it. So we are very interested in tweezers as well, not yet in the combination with molecules, but maybe that's something to think about. And especially in the context of a BEC, maybe loading a tweezer array from the BEC will be a fun way to create extremely large arrays of molecules. Leveraging this repulsive hardcore potential may allow us to really get localized single molecules. And perhaps it's a way to create molecular tweezer arrays with hundreds, if not thousands, of molecules. So with that, I want to conclude. focusing on the take-home messages, I think we are now sort of at the verge, or maybe even past that point, where we have a similar level of control over molecules as we have for atoms. We have real-time control over collisions and interactions in the molecules, and perhaps we see the onset here of new quantum liquid type behavior. We want to thank the group, really highlighting the work of our amazing postdoc Ian Stevenson, who is moving as a faculty to the University of Virginia in the summer. The wonderful work of the first generation of students, in particular also Niccolo Bigali, who was here the last time and was a huge driving force for a lot of the things I showed you. Next generation of students, also amazing driving force, Siwei Chang and Wei Jinyuan. And already the next generation who is here, Hanel Kwa and Asaf Tobrachi are doing amazing work in the lab, and you will hear of Hanel's work in a minute. Thanking all our collaborators, funding agency, and applied to Columbia. We are especially interested in postdocs. It turns out mostly for the tweezer experiment, so let me know if you're interested. And thanks so much for your attention.
Thanks for the talk. Any questions? Yeah.
Yeah.
So you showed the zone of the zone in which you essentially don't get three-body recombination,
right?
And how it switches on again when the shielding potential supports a bound state. I guess I was a little bit surprised that it switches on slowly rather than instantly, and you know, it drifts up from zero rather than I'd almost have expected it to appear at a larger value and then tail down. Is there an experimental reason for that, or you know?
Yeah, what I can say is since we have a detection limit here that kind of bounds us to measure, you know, we are not able to measure anything below 10 to the minus 24 centimeter to the 6 over second. We don't know really what's happening underneath here. So you're basically, you know, likelihood is, you know, there is some smoothness to it here.
No, but
we can't
it's
really
on the
see
other side of the dashed line that I almost would have expected it to appear at a large value and then tail off, because I guess I would
I see. Interesting.
I would have thought that the three body would be fastest when the bound state exists but is shallowest.
Interesting question. There is some, of course, there is some, you know, there's still a finite temperature correction also that needs to be taken into account, which I believe is actually part of why it behaves the way it behaves. You basically have a thermal dissociation, which is actually very important to take into account. You know, with Chris, we looked at that in quite some detail, and the thermal part is actually quite important. Yeah, we can discuss more later. Yeah.
Maybe time for one more question. Yeah.
Sebastian, thanks for the very nice talk. Just a technical question. You said the lifetime is set by, the one-body lifetime is 8 seconds.
Yeah.
And that's limited by just the trapping, the laser light?
Yeah, it seems that dipole trap or scattering from the dipole trap is dominant, but it's also possible that we are at the, you know, close to black body influence.
Okay.
So it's not an unusual sort of black body life, but we see actually quite a dependence on the trap still. But we haven't dissected precisely what contributes how much. So it would be great if it's a dipole trap, because then by going to a larger wavelength dipole trap, you should actually be able to push
1064?
1064, yeah. Yeah, we're considering, you know, trying out something else to see if we can push it, yeah. But it's, you know, 8 seconds is pretty good, especially compared to the interaction energy, which, you know, kind of corresponds to a time scale of like, you know, milliseconds or so.
Great. Beautiful results. In the interest of time, let's thank the speaker again.